think it's very apropos to have a discussion of solar structure in this meeting. So the question we want to ask is the sun this interesting? Or is it something more mundane and boring? And the question is, how do we find that out? In fact, my first paper with Michael was about inversions. And this was the time when this work was done in basically 93, 94, when there were very little data. There was just one data set, which was the Big Bear data set, which was fantastic, but still nothing compared to some of what we have now. And we were trying our best to get as much information we could out of that set. And so we did inversions for structure, for rotation, and anything else we could think of. And what I'm going to present are results, not just from the BBSO set, but everything that has come later. So the question is, what have we learned? We've learned about solar structure. We've learned about solar dynamics, which Rachel will undoubtedly tell you a lot about. We've learned about the physics in the solar interior, which is, I think, much more important. And we've learned of solar cycle changes. Now, most of the solar cycle, the really dramatic changes are in solar dynamics, so I assume Rachel will be speaking of those. The ones in structure are much more muted, much more subtle. I think Margarita will touch a bit on that, and I'll show you maybe perhaps one slide. So the question is, oh, sorry, I did the wrong one. Why do we need inversions? And that's because comparing frequencies does not work. And this is what this shows are the frequency differences between the famous, infamous, whatever, Model S and the sun. And these are the raw frequency differences. The color coding is just L's. I wasn't sophisticated enough to use, a continuous color bar, so never mind. And this is where we've scaled the frequency differences inversely with the mode inertia. And we find that most of this difference is a mode inertia effect, the fact that modes with low inertia are easily disturbed more than modes with high inertia. But there's this huge contribution here. We know today that all of that comes basically from a very, very thin subsurface layer. But of course, that took a while to figure out. And in fact, it's the surface term, as we call it, that can really hamper learning about the sun by just comparing frequencies. And a case in point is this. These are 4 models made by Jan. That's Model S. These are cousins of Model S, same physics, but different equations of state. And the question is, yeah, maybe looking at this, we can say this is bad, but which of these is better than others in terms of actually reproducing the structure of the sun? And hence inversions. What we do, we connect the relative frequency difference between a model and the sun to a kernel response and the relative sound speed difference between the model and the sun. Another set of kernels, the relative density difference between between the model and the sun, and a surface term which basically takes care of this trend. Now, I've shown sound speeds, squared sound speed and density. You can change this to adiabatic index and density. And what people have also done, and I'll show you some results later, do what's in the field known as secondary inversions, where you assume you know the equation of state, for example, and then try to figure out things like the composition. You know the equation of state and opacity and figure out the composition within the sun. Now, what do inversions really tell us? That's the figure I showed you before. That's the sound speed difference between these models and the sun. This one gives rise to this green curve, which we can say, yeah, it's not good. Okay, but the rest, I mean, they're not that dissimilar. So we need to figure out why, for example, these equations of state, why one equation of state does better than the other, trying to understand the differences. But inversions give us a more direct method. So what have we learned so far? The first thing is that our solar models are actually very good. Okay? Look at the scale here. That's a 0.5% difference. In any other field of astrophysics, this would be 0. We'd say we know the structure, let's forget it. But we are solar physicists, we believe in getting everything we know out of the data. And yes, so our models are very good. There are differences. So this is sound speed, this is density. These are just two different models with slightly different physics, the red and the blue. And so there's a big difference here. We'll come back to this a bit later. There's some difference here. But on the whole, we're doing remarkably well, which actually means that, okay, first thing is, since we've inverted for the relative difference between the sun and the model, the sound speed difference between the sun and the model, and since these differences are indeed small, we know the sound speed of the sun. Okay, and it's fairly model independent. We've done various tests, and the model doesn't really come through if it's a good model. Similarly, we know the density. Okay, so we know the structure, the primary structure of the sun. The mechanical structure, I must add, because as you saw in the inversion equation, there's nothing about temperature or metallicity or abundances directly. If you want to do temperature, you have to assume you know the opacities, which is, I'll come to the talk, a can of worms. Now, the thing that made helioseismology famous in non-solar physics circles is the solar neutrino problem. Now, people in the audience above a certain age know solar neutrino problem intimately. It dominated our lives for many, many decades. And there's some people who were, I think, here from the very beginning of the problem. But this is one of the few problems that has been completely solved, at least as far as solar physics is concerned. What was the solar neutrino problem? That solar models predicted more neutrinos than were observed. So these yellow bars are predictions of solar neutrinos, predictions that would be the capture rates for different neutrino experiments. Like chlorine stands for the Homestake mine experiment, where the detector is basically chlorine. Similarly, this is heavy water. This is water, the Kamiokande and Super-Kamiokande, gallium, sage, and Galax. And this is the deuterium, which is the Sudbury Neutrino Observatory. Now, for very long, decades in fact, people thought the problem with the solar neutrino problem was we could not model a sun properly. And people tried to do all sorts of things to get the neutrino emission right. But then came helioseismology, and we saw this. Okay? We know the structure of the sun. If we'd mucked about with the model of the sun, we will no longer satisfy. We will no longer have a model that is very close to the structure of the sun. In fact, if we wanted to get just the beryllium neutrinos right, this is the difference, a slightly different model, but if I wanted to get this model to have the correct neutrino flux, then the sound speed of the core would be, the difference in sound speed would be at the 10% level. We would have seen it. We don't. In fact, this is what we see. So the solution, of course, we know turned out to be that neutrinos change flavors, they have masses, and since Sudbury can actually detect various flavors of neutrinos, we know now that our predictions are a bit embarrassingly they agree with the observations. So in some sense, in the solar physics community, in the astrophysics community, the solar neutrino problem is a done deal. It's not us, it's them. Though they really wouldn't believe us till we had the confirmation from the Sudbury Neutrino Observatory. But it's one of the few examples where we could show, thanks to seismology, that our models are actually darned good. Okay. So the fact that the models are really good helps us test different physical processes in the sun. And I'm going to show you a figure that Bill has shown before, which is that we need diffusion to actually get the structure of the sun better than what you would otherwise. And the fact that we have diffusion, that we need diffusion, solved a number of problems. One is the amount of helium in the solar convection zone, which can also be found using seismic data, and the depth of the convection zone, because having diffusion increases the depth of the convection zone because the heavy elements increase opacities. Now, at the same time, and in a few years, secondary inversions by Sasha Kusovichev actually showed that this is the hydrogen abundance. The hydrogen abundance is not flat and then decrease in the core. So that's the non-diffusion standard model, but in fact has a decrease. Now, he did have to assume he knew the equation of state and opacity. So the real error bars are probably larger. On the other hand, it is definitely not flat. So we know that. And if you look at it carefully and compare it with standard models with diffusion, you'll actually find that this decrease is far gentler than the normal diffusion models that you find. So in a sense, even though Sasha did not comment on it, this is an indication that there are other mixing processes inside the sun, particularly at the base of the convection zone, and that actually would also take care of that finger-like structure in the sound speed that you saw. Okay. You'll see that none of these results is particularly new. That's because structure inversions have been so successful that they're no longer used to study the sun per se, but other stuff, which I'll come to later. So what else did we learn? That there is a slight asphericity in the sound speed in the outer regions, that the equator has a lower sound speed than the higher latitudes. And I wanted to show this particular graph because Michael was involved in this paper. And what we've also learned is that the asphericity changes with solar activity. This is the average asphericity at very close to the surface as a function of time. And solar minimum was black, solar max is here, and you can see the shape changing. So there is, at least in the outer layers, there are signs of changes with activity. Now, Rachel will show much dramatic changes with solar activity when it comes to dynamics. Structure is much more muted, okay? What else can we learn? Equations of state. So Julian Elliott and Sasha Kosovichev showed that the then opal and MHD MHD equation state, made models where gamma 1 did not agree with the sun. Now, this was surprising that the disagreement was in the core, because you thought, oh, core, ideal gas, gamma 1 is 5/3. Why on earth is it not agreeing? Part of the problem they later found, and the equations of state have been corrected, is that there are a sufficiently high number of electrons that are actually relativistic. Remember the Maxwell-Boltzmann tail. There are enough electrons in the tail which are relativistic. Relativistic gases have a lower gamma 1 than normal ideal gases, non-relativistic gases. So that actually lowers the gamma 1 in the sun compared to our models. So this was seen, and both projects, Opal, Forrest Rogers went and immediately corrected it, and also MHD has been corrected. So we know that. Now, closer to the surface, you can actually do an inversion for gamma 1. Now, the problem with the adiabatic index is it does depend a bit on other structural parameters of a model. So you need to extract that bit of the adiabatic index that only depends on the equation of state. And you can do that and invert for that. And we did that many years ago. And we could again show that, yes, indeed, the Eddington, Faulkner, and Flannery equation of state should not be used. And I was really shocked to learn that many people in the stellar physics community use it even today sometimes. And the others, they have various problems, some better than the other. We know some of the reasons, but not all. A lot to do with how the hydrogen atom is treated. So studying equation of state is difficult because just because there's this gamma 1 difference, you can't go and say, add this difference to your tables, because you have to make sure that the equation of state still obeys Maxwell's relations. So you have to be self-consistent, otherwise it's not an equation of state. So what's the current issue? The solar metallicity problem. Yeah, there's some people who call it the solar model problem, but I think it's a metallicity problem. What's the problem? In 2004 and 2005, a group led by Martin Asplund used 3D simulations as atmospheric models and said the solar abundance is much lower than what we had been using. So the Greves and Soval 98 is Z over X of 0.023. And in 2005, Asplund et al. Lowered it to 0.0165. And that immediately made the models far worse than the sun, mainly because these have really shallow convection zone depths. There are other subtle features, like the helium abundance is all in the convection zone is also much lower. But the most striking feature is the base of the convection zone, which causes this large increase in sound speed. Now, Asplund et al. Went back and redid things, and then they increased their estimate to Z over X of 0.018, which of course takes care of a lot of the problem. And then there was the issue, another group led by Elisabetta Kafau. I thought I saw Tom here, Tom Ayres here this morning. He was part of the group, and they did the same thing. They took 3D simulations of convection, and they did their own abundance determination and came up with a higher abundance. So what's the abundance of the sun? If you do not know the abundance of the sun, you do not know the abundance of any cosmic object. So what's responsible? So recently, Gael Bulgen, and he started doing this when he was a student. Now he is in Leuven, I think. Decided to make models changing one physical element at a time and doing the inversions. So this is where he keeps the abundances to the higher of the Asplund abundances and changes the equation of state. Yeah, slight, but not much improvement. This is where you keep the equation of state and opacities constant, but change the abundances. Yes, of course, that improves things. The moment you use GS98, or what they've also done is taken the Asplund abundances and increased the abundance of neon. This was a suggestion put forward by, this was a paper John Bacall, Aldo Serenelli, and I had written many years ago that you could actually get rid of the problem by increasing neon. And sure enough, you do it, but then later we found neon actually produces some problems, but those are so subtle that maybe we shouldn't bother. Here, the opacities were changed, yes. There's a slight difference. And here the diffusion formulation was changed slightly. Not much, okay? So clearly equation of state and the known opacities don't help. Gall had the one really new part of this work, which was, I thought, very clever, was to invert for an opacity proxy given by this quantity. And it's not a pure equation of state thing, though it is dependent on the equation of state, but it also has, unfortunately, abundances in it. But still, what you can see is that the only thing that really matters is abundances. So they looked at the stability criterion, which Sasha Kosovichev had looked at way back in 1993. What is the stability criterion? It's this chap, which is you expect a flat difference at the convection zone base. A is flat in the convection zone and then suddenly rises at the base of the convection zone. So these are differences in A. And again, doesn't really matter. So what do we do? Opacity. So Nuria Vignoles, who is a student of Aldo Serenelli in her PhD thesis, looked at detail into some of the sources of errors in stellar models, including errors caused by inversions when we get the solar results out. And she looked carefully at opacities. What would be the contribution to the sound speed difference if you changed, for example, the opal opacities to OP opacities? Some OP opacities are marginally higher, not much. What happens if you increase the opacities at the base of the by 7%, not just at the base of the convection zone, they just increased it. The 7% number came from an experiment I'll talk about very soon. And then she took into account all other errors, but the total amount is 0.2%. It still doesn't give you the required change. So at least opacities as we know them, the sources of errors as we know them, doesn't do the trick. Of course, you could take the extreme view and say, what if we assume that the entire sound speed difference is because of opacities? And you can do that and find the difference in opacity. And Jan can correct me, but you got about a 30% number. Yeah, a bit more than 30% change in opacities. So how do we know the opacities are correct? People are trying to measure them. So in 2015, Jim Bailey et al. Did one experiment at the Sandia Labs to measure the opacity of iron at the conditions at the base of the convection zone. Their results did not match theory, or rather theory did not match their results. And there were issues in the sense people raised questions. A, can they reproduce the results? B, are there any systematic trends? Because most of the anomalous results were believed to be because iron in that region has an almost neon-like structure, except it has one vacancy in the L shell. So if this were full, it would be a neon structure. So what the group did again, so Jim Bailey is, I believe, the second author in this one, they looked at two other materials. They looked at nickel, which has no vacancies in the L shell, and chromium, which has 3 vacancies in the L shell. And they expected they would get the highest discrepancy between theory and observation for chromium, the next highest for iron, and the next highest for nickel, if their hypotheses about why theory is going wrong are correct. Of course, life is never simple. That's the pseudo-continuum for chromium, iron, nickel. Chromium matches, nickel sort of matches, iron stands out like a sore thumb. This just shows different experiments that they can actually reproduce the line shape. This is a nickel transition. These are various opacity sources calculating the line shape without experimental broadening of the lines. they've only drawn the ones that sort of match the data. So yes, our theory is still deficient, and the culprit are probably how ions behave in a plasma medium. At least that's what the authors think now is the problem. So what can we do about opacities? Because these are difficult experiments. Calculations of opacities are even more difficult. Maybe go to neutrinos. If errors in, we've only looked at neutrinos from the PP chain so far. Those are the most well observed neutrinos. But people are beginning, particularly the GALAX experiment, the Borexino experiment, are beginning to look at CNO neutrinos. Now, the errors are still too large, but if you look at just the PP neutrinos, then this is the high metallicity standard solar model. These are the low metallicity standard solar model. And the Borexino result is this green circle. This global is where you use helioseismic constraint as well as neutrinos. By helioseismic constraints, I mean the base of the convection zone and helium. So again, Nuria did simulations to look at the differences in the CNO fluxes for high Z models versus low Z models. And they're well separated. They did a Monte Carlo, so they're quite well separated. And actually, Douglas Goff had a paper recently where you could show that the CNO neutrino should be directly related to the heavy element abundances. So we are basically waiting for CNO observations to get better. The error bars are still too large. Once the observations get better, I think we would have a completely independent view of whether the problem is indeed a metallicity problem or a modeling problem. So we are at a stage where we know the structure of the sun, and we're trying to figure out details of the structure and the physics, and including some things like the metallicity, which we had taken for granted. So I'm going to end by leaving you a few thoughts, and I'll be happy to take questions. A, we know the structure of the sun quite well. Yes, I would say we don't know the structure of the sun of the outer 1%, where we really need good high degree modes to get that, but mostly. We've been able to constrain some of the physical processes, and we're trying to constrain them even more, like mixing processes and fusion. And did we ever have mixing in the solar core when it was when the sun was very young? That's a second level problem, but we still have problems with microphysics inputs, and those affect the solar abundance problem. Do we really, how correct are our opacities? How correct are our equations of state? And opacities are the biggest problem right now, but even the equations of state are not the best. There's still issues. And of course, these are microphysics, so diffusion, what are the diffusion coefficients like? Do we have, even in the conditions of the sun, do we know the diffusion coefficients properly? It's assumed it's a 10% error, who knows? And also, does radiative levitation play any role in a star as cool as the sun? So those are the problems that we are tackling with structure inversions right now, and so stay tuned. Thank you very much.
We have time for some questions.
Ryan, I had a hand up.
Thank you for a very nice talk. The last results you showed with the neutrinos, was that based on helioseismic models or evolutionary models?
Those were evolutionary models. Those are just a high Z standard solar model. Yeah.
So the opacities are very different.
So the opacities would be very different. Yes.
Different
but yes, the question is, how much do opacities affect neutrino observations? And It's not clear they do much in conditions of the core because there the opacity is supposed to get simpler. But we'll know. Yeah, thank you.
I wonder, what is the justification for ignoring the magnetic field?
Mainly that, so we do have signatures of magnetic field in splittings of helioseismic frequencies. And those splittings suggest that, at least when it comes to structure inversions, all the effect is from the very shallow layer. So the splittings are not deep enough, are not big enough to suggest changes that are deeper inside. So.
Okay.
This sort of brings me to this naive question. Why 20 years later, we still haven't solved the surface problem? We still do our frequency computation by just ignoring that we're not doing it right at the surface.
Oh, actually, there's a lot of work going on. And there, the motivation has been astroseismology. There's been work going on in multiple places, trying to see how much of the surface problem can be solved by convection simulations, how much of it is actually non-adiabatic effects and frequencies. So the work is going on, but it's not simple.
In the same spirit, may I ask, in your description of how the structure varies as a function of latitude, was any account taken of surface effects that vary with latitude? As we know, magnetism does, at least surface magnetism.
Yeah, so that was fully, so the Antia, Chithre, and Thomson result was a fully 2D inversion where everything depended on latitude and longitude. Though, to be fair, because the even order splittings depend both on magnetic fields and on magnetic structures, they had made the assumption that the entire asphericity is almost completely due to due to sound speed variation. You could flip the question around and say, what's the magnetic field if you assume everything is magnetic fields? Yes. And the other plot, which was time variation, yes, those were independent. Those were actually ring diagram results, but each of them had their own surface effect taken into account.
We have to move on now, so let's thank our speaker one more time. Thank you, Savani. Next, we have Rachel HAO speaking on solar rotation. What's this one? So there's an advancer and a laser pointer. It takes a few seconds.
Well, good morning, everyone. It's a great honor for me to be asked to be asked to talk about the solar rotation, which was such a central part of Michael's work. So I have like 25 minutes to cover about 30 years of science. So this is going to be rather a whistle-stop tour. But so I'm going to look at it under four main headings. First, a brief introduction to rotational splitting and the inversion problem. Then a quick tour of the solar interior rotation. Something about the temporal variation. And finally, a quick mention of the solar rotation project, which has already been mentioned this morning, that Michael initiated a a couple of years ago. So, start with the rotational splitting. I thought I'd show you a picture of a rotationally split mode from the Bison observations, which is basically the plot that I showed at the Gong 94 meeting, which was my first visit to the US and the first time I met Michael. And I sort of presented this slides on the first morning of the conference. I was horribly jet lagged. It was my first time in the US, but I think it must have been Yvonne Ellsworth that introduced me to Michael afterwards, and we got talking in the cafeteria after lunch. We had a long conversation, and that was really the start of a collaboration that lasted for the rest of his life. So more than 20 years. And a few months later, went to work with Michael at Queen Mary and learned an awful lot about 2D inversions. So I hardly need to tell this audience very much about 2D inversions, but if you think that every oscillation mode of the sun can be characterized by its angular and radial spherical harmonic characteristics. And so different modes occupy different areas of the sun, and you can put them together to build up a profile of the interior. So the degree gives you a depth dependence, and the rotational splitting is what happens because the rotation lifts the degeneracy between modes of different M. And the modes of different M sample different latitude ranges, and so you get this, you can build up a two-dimensional picture of the rotation. How you describe this mathematically? I can't give a talk honouring Michael's work without including at least a couple of equations. And so these are kind of central to it. The inversion problem is basically to find the combination of the data that will give you a localized estimate of the internal properties. So for each mode, you have a sensitivity kernel, and you make a weighted average of those, and that gives you a weighted average of the rotation rate. So that bold K there is the thing that we call an averaging kernel, and what you're aiming for is to get a nice localized one. And then you can basically get an estimate of the rotation rate, which is a convolution, or it would be if there weren't any errors, a convolution of the real rotation rate with these averaging kernels. Of course, in real life, you have errors, and the errors also combine, blow up. And this work, so one of Michael's early papers, shows how you can balance the width of your averaging kernels against the amount by which the errors blow up. And somewhere in here, you get some kind of a sweet spot, which ought to be where you pick, where you get your inversions, where you get your best inversion result. It gets a little bit more complicated when you go into 2 dimensions, but it's a general idea. There are also other things that you might want to consider. This is from a project, which is basically the first project that Michael sent me when I went to work with him as a postdoc, and it's how I learned IDLs, which is to look at the error correlations in rotation inversions. And so it turns out that the top row is the error correlation functions for various inversions. The bottom is the averaging kernels for the same inversions. And you can see that even when the averaging kernels go nicely to 0 away from the target, the error correlations don't always. So you have to be a little bit careful about that. And having published that paper, I haven't really looked at that again, and I really should, and extend it to 2 dimensions. So having introduced the idea of how you do inversions, let's look at some results. Okay, Bill showed this one already, so I won't dwell on it, but here's Michael's inversion of the BBSO data, and you can see that there is differential rotation in the convection zone and some kind of shear layer at the bottom of the convection zone. And you notice that this doesn't really go to the surface because the BBSO modes didn't have high enough degrees. You can't localize things near the surface. And we get to the Gong data. Again, we've seen these. Oh, sorry, I've skipped. When we had Gong, we could see things rather better. And so you can see the near surface shear and the differential rotation in the convection zone. And that's from the Gong paper that Michael led, which Bill has already spoken of. Now, a little later, we did some similar exercises with early MDI data. Now, I'm showing these. If you look too closely at the high latitudes in MDI, you can see some funny things going on, which is a bit of a cautionary tale because we got quite excited about these, what we looked like a jet. And eventually it was decided, became obvious that really what we were seeing was the effect of systematic errors in the Gong, in the MDI splitting coefficients. So all the understanding of averaging kernels in the world won't help you if the input data are wonky. So that is something that you need to bear in mind when considering inversion results. Let's move on to take a quick tour of the rotation of the solar interior. So this is just an average of all the HMI inversion profiles that I've done. And so you can see the general features. We have the radiative core, which these inversions can't really speak to. The radiative interior, which looks fairly bland. The convection zone, shear layer at the bottom of the convection zone, known as the tachocline. The convection zone and the near surface shear layer at the top of the convection zone. So I'm going to look a little bit at each of these in turn. Right. So, sorry, I'm going right. Okay. So what can we say about the core? Actually, not as much as we would like. It's rather hard to constrain because only the lowest degree modes penetrate to the core. The modes of radial, dipole, maybe quadrupole modes, and of course the radial mode doesn't tell you anything about the rotation. And you can only resolve the ones at the very low frequency, which didn't have terribly high signal to noise. And even those modes, they only spend a tiny fraction of their time in the core. So the average they get is really highly weighted towards the near surface rotation, and your estimates of the core rotation are quite sensitive to any errors. And so really, after a lot of discussion, we need G modes, which unfortunately have very low amplitudes at the surface, and we don't have a fully accepted measurement of them in the sun. And there's plenty of stars where you can see the G modes beautifully, but the sun doesn't work like that. I just wanted to show you a plot showing some estimates of the rotational splitting as it sort of evolved over time. And you see it sort of converging on something close to the near surface rotation rate. So moving on to the radiative interior, basically, well, we again, we can't resolve that terribly well. As far as we can tell, and I think the best work that I know of was this paper by F. Darwich et al. In 2002. It's pretty uniform, at least down to, as far as we can tell. We can't rule out some fast rotation in the core, but between the core and the bottom of the convection zone, it really seems to be fairly bland. When we move on to the tachocline, things start getting a bit more exciting. We've got better resolution there, and it's of interest because it's believed to be the seat of the dynamo, at least in some models. I know there's arguments about that. So, but it's not really resolved by the mode. So you have to apply some extra cleverness to get to constraints on the shape and size of the tachocline. And a lot of people worked on this and came up. Basically, it turns out that it's the thickness is a few % of the solar radius. And the depth is fairly well constrained. And this is interesting because if it was as, it's quite difficult to get something that's as narrow as that sort of stable in a simple model. So it's a challenge for the theorists to explain how it stays that way. And is it spherically symmetrical? Well, according to this work by Basu and Antia, it appears to be prolate. So it's shallower and wider at high latitudes than near the equator. So that's the tachocline. Moving up into the body of the convection zone, we have, if you look at the slope of these contours in the body of the convection zone, well, the first thing you notice is that they're certainly not parallel to the rotation axis. And I can remember just around about the time I came into the field, this was still kind of a controversial result. And some of the modelers would really have liked them to be parallel to the rotation axis. But they really aren't. And in fact, if you, as was pointed out by Peter Gilman around about 2002, if you measure the slope of the contours in the rotation in the convection zone, they sit quite close to about 25 degrees to the rotation axis over quite a wide range of latitudes. And this, I believe, is something to do with the Coriolis force acting on the rotation and the meridional flow. So there's the general shape of the convection zone, and then near the surface we have the shear layer, which now this was the subject of some work that Michael did with Thierry Corbard, and they measured the steepness of the shear layer as a function of latitude using F modes from MDI. And the beauty of F modes being that they go right to the surface. And they found a couple of things. One being that if you look at the sort of d log omega by d log r, it turned out to be pretty close to -1 at the low latitudes. And that's interesting if it was purely a fluid dynamics problem and you were looking at conservation of momentum, it would apparently be more like 2. So that's telling you something interesting is going on. And then apparently it went more shallow at higher latitudes. But that result has been updated by Barakat et al. In 2014, looking at sort of more modern reanalysis of the MDI data. And it turns out if you use the reanalyzed MDI data and throw out the really high F modes, really that sort of change in sign doesn't happen. It pretty much goes away and it stays pretty close to -1 for quite a high range of latitudes. So again, that's a reminder to be careful of your systematics. Having said that, move on to the temporal variation. So just for fun, I took all the inversions of Gong data and animated them. And you can see that things are moving, but that kind of animation is not all that informative on its own. But, there we go. If you take out a temporal mean and smooth things a bit, then things start to look rather more interesting. So now you can see that we have these bands of faster and slower rotation, and you can see these bands coming down towards the equator during the solar cycle. There goes cycle 24. And is anything happening? Oof. There is cycle 25. So sort of stepping back a bit to, okay, the first point, I mean, this effect of bands of rotation marching towards the equator had been observed at Mount Wilson since the 70s. But with Gong and MDI, we were able to show that it was actually penetrating into the bulk of the convection zone, at least in the upper layers. So this is from 2000, and this is, Michael was very involved in this work. I have happy memories of sitting in Yuri's lab at Gila, and Michael would say, you know, plot it this way. Let's, you know, sort of try it that way. And I produced piles of plots, and eventually these papers came out. And I continued collaborating with Michael on this work right up until last year. So this is the Vorontsov et al. Result that Bill showed, and you can see very beautifully how these bands penetrate into the convection zone. And they also had the idea of characterizing it as a harmonics of the solar cycle, which was an interesting thing. Not all these results held up. That they had a third harmonic, and when we looked at it later, it sort of seemed like the second harmonic is much more interesting. But so, as I said, we my last paper on this that had Michael as a co-author came out last summer, and yes, I very, very much valued Michael's input on this. And without him pushing, it might not have been published until much later, because we had a certain amount of difficulty with the referees, convincing them that this little signal here was really the signature at the beginning of cycle 25. I think if you look at the very latest data, you know, it's very obvious that the new cycle is coming. And just to show that I'm not the only one that works on this, here's some very nice plots from a recent paper by Basu and Antia, which is, I think, still only on archive, but is coming out in AppJ. Oh, congratulations. And so these go well down into convection zone. You can see how this signal penetrates well into the convection zone, and very beautiful result. And just as a reminder, finally, My other workers, just to remind you that, in fact, though I show you all these beautiful symmetrical plots, in fact, the thing is asymmetrical. It just gets symmetrized by the nature of the inversion of the global inversions. So, and so that was the temporal variation. If you want to ask me about what's going on at the base of the convection zone, I can show you a slide later. So finally, I wanted to say something about the solar rotation projects, which was Michael's initiation. So to go back to where we started, here's a plot showing the rotational splitting from 16 months of bison data. That's exactly the same section of the spectrum from 42 years of bison data, which gives you an idea of what we can gain in terms of resolution just by longevity. And that's one of the reasons why it seems worthwhile to revisit the rotation profile now that we have so much more data than we did when the first light papers were published nearly 2 decades ago. So Michael invited a very international, wide-ranging group of people to collaborate on this. And you can see there's people from many countries involved. And basically it proceeds by telecons. We hadn't got all that far at the time of Michael's untimely death. We were still discussing what data we should work on. We've made some progress since under Jan's leadership. We've identified a set of data that we, at least for a first cut, we want to look at, which is 6,400 days of data from HMI, analysed by Sylvain Kozenik to give splittings just from that data as one thing. And we're trying our different inversion techniques on it. So I invited colleagues to send me their inversions, and okay, this one is from Antir and Basu. Beautiful plots. So there's the rotation as function of radius at different latitudes plotted. Sergei Vorontsov sent me these very beautiful plots. And this one's mine, which is rather blander than the others. I'm trying to do the trade-off parameter exercise. And what that's telling me is that I should have rather more regularization than I'm ever used to using, which gives me a rather bland inversion, particularly at high latitudes. But so there's obviously a lot to discuss. I mean, some of the things we are interested in is how well we can constrain what's really going on in the in the radiative interior and in the core. And indeed, is a tachocline really prolate? How much damage, what are the systematic errors and how much damage are they doing? What does the near surface shear really do at high latitudes? And in fact, the general idea is to produce the most definitive profile of the solar rotation that we can. So, my conclusions. So we would really like G modes to measure the core rotation. As far as we can tell, the radiative interior is uniform. The rotation in the convection zone most certainly is not on cylinders. The rotation in the near surface shear is has this d log omega by dr of about -1. And the tachocline isn't resolved and appears to be prolate. And finally, so helioseismology can tell us a great deal about the solar interior rotation. And we should always remember to check our averaging kernels and watch out for systematics. And stay tuned for the improved definitive profile coming sometime in the next year or so, I hope. Thank you.
Thank you very much, Rachel. Questions? Don.
What is going on at the base of the
Doesn't.
Sorry. What happens at the base of the tachocline?
Okay. I may have to come out of slideshow mode for a minute. Okay, here we go. That's okay. So this is at the equator. The top row is just above. The bottom row is just below the base of the convection zone. That's is the result from Gong. The first, you can see this, what would appear to be an oscillation in the first few years. And we can also see that there's nothing as sort of periodic as that going on later on. Oops. Oh. What I'm trying to do is show you. Sorry. Okay. There we go. So overlaid it. So that was Gong. If you overlay MDI, you can see that there's a general tendency for whatever is going on is happening in MDI and HMI as well. But not everybody agrees that there's really anything very much going on at all. That's from the Basu and Antia paper, and they don't see much variation. So it is controversial. We sort of agree to disagree about it. And certainly there doesn't seem to be anything terribly periodic going on anymore.
Another question? Yuri?
Have you published that strip? Will you publish it, please?
Yeah, maybe in the proceedings to this meeting, if nothing else. But it's been about 10 years since I updated that one. So I think I had a plot on it at the AICS meetings.
One more question from Sasha. Sasha Broom.
Rachel, you mentioned that you are seeing through the torsional oscillation the beginning of solar cycle 25.
Yeah.
Can you give us the precise date that you are seeing? I mean, in month, is it late 2018, early 2019?
Hang on. I'm trying to. Oh.
Because we just had, the NOAA NASA forecast, and so I wanted to see
It's
how it fits into that.
Okay. Well, that's my latest plot. Oh, what's here? All right. Okay. So, yeah, I mean, it started. This plot goes up to about 2 months ago. So it's become really strong by mid 2019. I think it's really only in the last few months that it's sort of become really through the bulk of the convection zone. Before that, it was more a little bit shallow and disorganized, looking deeper down. But certainly within the first half of 2019, it's become very well organised, and really for the last year, it's been pretty definitely there.
Okay, thank you very much. Let's thank Rachel one more time. Next talk is by Sasha Brun. Read the title for you. Dynamo action and sun-like stars.
Allez. Tested it, it worked normally. System is slow. Yeah, so just to start, it's of course an honor to be here and to make a presentation in honor of Mike, which was a good friend and was visiting us often. If he wants to show that. We tested it, it worked. Let's see.
Can you re-initialize?
Escape. Maybe we see the switch to here. It was exactly the same setup. What's going on?
I don't know. This is this one.
Here we go. Yeah. Okay. So yes, I was asked to talk about the solar dynamo and let's say what I call the evolving solar stellar dynamo, a tribute to Mike. This work was done a lot with Yuri and Mark here in Boulder, and also Kyle and few other young people who have joined my team in Paris. So I want to go on. And so here, for instance, a picture of Mike during a school of a project that was called Spacing, for which Marcus and many around us have been contributing to. And so we organized this school in Saclay, and you can see that Mike is giving the lecture here. You can see Mike here also at the cafeteria in Saclay during a lunch of our research group. And more recently, here at a barbecue party we organized in a house we rented just before going to the total solar eclipse in 2017. There are many other pictures, and you can even hear Mike. This is, a moving image. So we were very close. He was visiting us often in Paris, and we miss him dearly, like everybody. I also wanted to tell you a little bit about his passion for EC in Bern, and eventually he would have been also in China if he would not have passed away. So here are two books he also published. So one with Jean-Paul Zahn, who's also we lost, unfortunately, a few years ago. And I was a young scientist invited to that conference. And a few years later, I was organizing it with him. And he chose to pick one of the simulations we did with Yuri about the solar convection zone and the radiative interior because he liked it. And because of that, I wanted to show you this movie, which I don't think everybody has seen, of a very extensive simulation, 99% of the sun from R equals 0 to 99%. And you can see the very small stuff at the surface. We have a very high resolutions, like a 4,000 cube simulation. You see the small stuff and how this is the entropy field. You see we are in the equatorial plane. You see that the downdraft merge into longer and larger cool structure, and you see the gravity waves being excited. And of course, Mike was really interested in understanding the physics of the gravity waves and their detection. So regarding the work that inspired mine, I would like to mention few of them, and I will go through my talk about part of these points. So the first one is the fact that, as has already been seen and shown by Rachel and a few others earlier, like Bill, he has worked a lot on the internal rotation of the sun, and from the science paper in '86 to the annual review of astronomy and astrophysics with Jorn, Mark, and Yuri, we all were working on this very difficult problem of understanding the solar differential rotation, that is key for the solar dynamo, as you all know. He also was among the first, following a work by Yuri and other people of his group. We have the meridional circulation being multicellular. For many years, when we modelers were showing our simulations and the meridional flow we were having in our simulation, people were doing helioseismology inversion would not believe them because they were multicellular, and they were a very strong feeling and in the community that the solar meridional circulation should be 1 cell per hemisphere. And the work of Mike in 2007 triggered an interest for people to look again at that. He also worked on trying to constrain with our Indian colleagues, Kumar Chitri and Antya, about trying to set up an upper limit on what could be the magnetic field at the base of the convection zone. And in this paper, he pointed it to a value about 3,300 kilogauss, please. Sorry. And so also more recently, as was said by Bill, he went into extending his work to other stars with the revolution of asteroseismology. So, of course, I've been working on the modeling part of these aspects, and I will show you a little bit of that. So I'm not going to insult you by showing you and explaining you the sun. Okay, you know that we have the cycle, we have a differential rotation, and what's difficult and was not anticipated is that the solar differential rotation is not cylindrical, and I will come back to that, but more like conical at mid-latitude. And also here, the work of Zhao in 2013 and the work of Mike with his postdoc showing multicellular meridional flow. So we know the sun is a complex chaotic system with a lot of turbulence in its near surface layers and in the convective envelope. And what's difficult to understand is not the magnetic field generation at all scales of the convective patterns, but it's the large scale organization. And that's what's tough to explain. So what can numerical simulation tell us about solar magnetohydrodynamics? So I will go briefly on the differential rotation and meridional flow, on dynamo and Villiers-Vernier cycle, on the sun in time and the solar-stellar connection, and some future development. And part of this can be seen in a living review in solar physics that we wrote with Matt Browning, one of Yuri's former PhD students, and in an extensive way if you are interested by these topics. So I'm going first on the differential rotation and meridional circulation aspects. So when I arrived as a postdoc here many years ago, more than 20 years ago, with Yuri, we tried to tackle again the problem with the differential rotation, and we are trying to get solar models that could have some resemblance with the observations. And we were reasonably successful in the sense that we were able to get a fast equator and a slow pole, but we were not as conical as the sun was showing us to be. And as I said already, the meridional circulation pattern that we were seeing were multicellular, and at time people will not believe that. And but from the beginning, the simulation were seeing so. So it's interesting to look at how the energy is flowing into such systems to try to understand it. And so what's going on is that you have internal and potential energies, you have Reynolds stresses, and you are triggering through various correlation a differential rotation, and with the Coriolis force, you have a meridional circulation. And we have now learned through work that we have done with Yuri and Mark and few others, that the meridional circulation is a response, an answer to an imbalance between the Reynolds stress and the viscous flux, that is very negligible in the sun, but in our simulation is not. So there is a balance between meridional flow and the Reynolds stress that really exceeds. So it's what we call gyroscopic pumping. One thing to explain why people were anticipating the solar differential rotation to be cylindrical, which turned out not to be the case, is what we call the Taylor-Prudman theorem. And if you take the vorticity equation, which is the curl of the Navier-Stokes equation, you neglect a lot of terms, viscosity, baroclinicity, and even Reynolds stresses by assuming that this is mostly dominated by rotation, you end up being cylindrical. You have no variation of the differential rotation along the z-axis. But it turns out to be wrong, and one of the things that we have been put forward through various modeling is the fact that there is a baroclinic effect due to the crosstalk between density and pressure gradient that lead to a latitudinal variation of the entropy field. So we did work with Mark and Yuri in 2006 in trying to see how much were we controlling the differential rotation and the amount of entropy variation, because the sun is stratified, so it's better to speak of entropies and temperature. So we did a set of experiments, and I will show you that. So this was the case I just showed you a few slides ago, which was reasonable in trying to reproduce the sun, but was not as conical. And that case had a 9K temperature contrast at the base of the convection zone, which is not a lot. I recall you that at the base of the convection zone is 2.2 million degrees. So we are speaking of very small variation of temperature here, but it's coherent. And so we play the game of controlling better our thermal boundary condition at the base of the convection zone. We started by putting a constant entropy, and the variation in temperature was only 3 Kelvin. And you can see that the profile is much more cylindrical. And then we play the game of increasing this forcing up to being almost disk-like for differential rotation. So we pushed it a little bit too much. And so the best case that we call, whatever is named, more realistic and closer to the sun was around 10K. So you see, this is very difficult because you need to do a very extensive simulation of turbulent convection, and you need to capture a 10-degree variation at the base of the convection zone. And if you get it wrong by few Ks, you get a different answer. So this is a tough problem. And I think one problem that we have been looking to work on with Aaron, Laura, and few others, I will come back to that, to a big European project we just got, is the convective conundrum. Is the fact that when you increase the degree of turbulence of your numerical simulation, you change the Rossby number of your simulation and you tend to become anti-solar, which is really not really nice. Usually when you improve the physics of your simulation, you will expect to get a better result. And it's not the case. And one of the things we are wondering about is how well are we controlling these various thermal boundary conditions. So now I move on into the solar dynamo and 11-year cycle. You can take, since Mike liked equations, I put a little bit like Rachel, you can get a good estimate, a first estimate, by looking at some force balance in the Navier-Stokes equation. So one thing that you can easily do is to say, what will be the equilibrium field if I was equilibrating the magnetic pressure at the surface with the gas pressure? That gives you a first scaling. You can go into the Navier-Stokes equation and look at more advanced scaling. For instance, you can say, okay, so Lorentz force is going to compensate the diffusion, and that gives you that the magnetic energy should be less than the kinetic energy. Then you can do what most of people assume to be the case, is what we call equipartition. You actually equilibrate. This is just a two-term balance, and we have published a work recently with Kyle and Yuri about more advanced 3 or 4 terms balance. But if you just do a two-term balance between Lorentz and advection, you will get equipartition, that magnetic energy is about the level of kinetic energy. If you make the sun rotate faster, like it is the case when he's younger, you will actually get into what we call magnetostrophy. Magnetostrophy It's just that you have the Lorentz and the Coriolis force balancing each other. And we leave the Earth is in a magnetostrophic state. The magnetic energy content in the Earth core is higher than the kinetic energy content. So we know that such system exists. And so when you get back in time with the sun, you expect the magnetic energy content to be quite large. So we have done several simulations over the years, and here I show you an example of a few runs we did back then, where we have some solution that barely decay first because it's a failed dynamo, barely grows because we are just at the threshold of the dynamo action. Dynamo is an instability, so you need to go beyond the threshold to trigger it. Of course, the sun has very large Reynolds number, and he easily excite that dynamo and maintain it. And you can get some solution, or you will have a linear exponential growth in a linear phase, and then the saturation. And how do you saturate the magnetic energy in the sun? This is one of the interesting problem, because what you have to realize is that today when you observe the sun, what you observe is the nonlinear outcome of a very complex convective magnetohydrodynamic system. So the differential rotation we see today is the result of a subtle balance between magnetic field convection and turbulence. So of course, if you were taking out the field from the sun, if you were able to do that, a bit like in a Maunder minimum, let's say with a lower level of magnetism, you will expect the differential rotation of the sun to be stronger than what it is. So where does this magnetic energy comes from? So as I said again, you have large reservoirs of energy. You have the luminosity of the star that get into your internal energy reservoir, and you have two main forces that drive the motions. And you will see that magnetic energy is difficult to get, and dynamo is a difficult process because you need a middleman. And the middleman is kinetic energy. There is no direct way or easy direct way to drag energy, to pull energy from these two large reservoirs directly to the magnetic energy. So you need to either have buoyancy driving, what's hot goes up, or pressure gradients. You know that the wind blows from high pressure to low pressure. And we have that in our system, in our convective star. And so you get this motion. And then through the work of the Lorentz force, you get magnetic energy. But what's subtle in this system is that to get magnetic energy generation, you need to get the work through the kinetic energy. But as soon as you have currents, you lose it through magnetic diffusion and ohmic heating. So it's why that's difficult. That as soon as you get magnetic field and currents, you want to dissipate them. But in order to replenish, it's not easy. And that's why dynamo is the next difficult instability to maintain. So we did several simulations, and the beginning of we were not including tachocline. This was that case, and the magnetic field was not so well organized. And then with the work of Matt Browning and Yuri again and a few others, we were able to implement a tachocline, and we were seeing the rise of the toroidal energy in the tachocline. And here you can see we start to have magnetic layers where you have the strong field organization. So more recently, we published a paper in Science with Paul Charbonneau and Antoine Strugarek. And here is a simulation of what you can do the best today in terms of convective solar dynamo, where you see that you have potential field line extrapolation, convective motions, differential rotation, magnetic ribbons being created, becoming omega shaped that could be the source of eruption and sunspots. And you see the process go on, and we start getting decadal long cycles and reversal. And you will see we started with blue on the top and a blue ribbon, and we are starting to get yellow lines at the pole and a red ribbon, and we got through a reversal. So here is the sequence of this reversal. You see, we can get equatorward propagation of the magnetic field and a very nice organization. So we are starting to be in a situation where we are starting to get convective, nonlinear dynamo solution that produce decadal long cycles. So we are making progress. And I will come to you later to the point where we are still failing to do a few things. And one interesting result that we also got with Yuri and a few other colleagues like Kyle is to be able to get some of this dynamo to shut down and get into a Maunder minimum-like situation. So here you see the butterfly diagram, equatorward propagation, and suddenly we start losing the organization of the cycle, and then we recover from it. And here, when we look at the quadrupole and the dipole and the interplay and the beating between these two modes, we find that when the quadrupole starts to upset the dipole, we find that the simulation can go into a Maunder minimum-like. And the reason why we were able to get this solution is that we were able to play some numerical trick to push a numerical simulation at low magnetic Prandtl number. And that's one of the difficulty of the dynamo simulation, that the solar atomic value of the magnetic Prandtl number is 10 to the minus 5, and we can barely do better than 10 to the minus 1 or 10 to the minus 2 in the simulation right now. So we know that if we go to more intermittent state, we have to go to more realistic parameters. So now that was the sun. The sun has a Rosetta Stone to understand stars and vice versa, to look at stars like with asteroseismology or spectropolarimetry to try to understand the sun in time. And that's what I'm going to tell you a little bit about. So recently, with Yuri and few others, we discussed the idea of trying to pave the stellar parameter space by doing not only a solar-like star, but going from K stars, K dwarf to almost F stars. And so we have starting paving the Hertzsprung-Russell diagram with a lot of different simulations, and here are some examples of them. So we go, for instance, for 4% of the solar luminosity to about twice the solar luminosity. So we have done a numerical simulation. Of course, this one cannot be as resolved as the most advanced one we do for the sun, because you have an extensive parameter study to do in 3D, and it's very costly. So here you can see we go from various rotation rate and Rossby number. We do have some clues on how differential rotation changes with global stellar parameters. We know, for instance, that there is a very weak trend of the amplitude of the differential rotation, delta omega, with the rotation rate. Some people say that they could be stronger, like Donahue et al. In 1996, but I think there is now a consensus that it's not too large a dependence. So it means that if you rotate your star faster, you will have a slight increase of the differential rotation, but in absolute value, but in relative value, it will not be the case. What seems to be more in agreement is when you go to shallower convection zone, when you go toward the F star stars, you seems to be getting stronger differential rotation. So what do we get in this setup of 15 simulations that we have done? What's very interesting, that we have found 3 states of differential rotation in stars. We have found the solar-like differential rotation, fast equator, slow pole, transition to solid body rotation. I have to say that all these simulations include tachocline. We have found a very interesting behavior, which is the anti-solar differential rotation. And we have been able to identify at which location in parameter space you can get anti-solar. And we have designed a simulation such to determine the limit between fastly and anti-solar rotation. And then we also find, for very fastly rotating simulation with a very low Rossby number, Jupiter-like profile. So it's not completely impossible that very fastly rotating stars actually look more like Jupiter with alternance of fast and retrograde jets, rather than having a monotonic decrease of the differential rotation as a function of latitude. So when we look at the scaling, and here this is as a function of fluid Rossby and delta omega, and I've put the half solar mass, 70%, 90%, one solar mass with some work from Ben, 1.1, 1.1, 1.2, and 1.3 with work we did on F stars with Kyle. We see that as we increase in mass, we indeed find stronger differential rotation. So we kind of agree with observations. As a function of the Rossby number, when we rotate faster, we tend to have slopes that are stronger, steeper than what the observation is telling us. And we have an understanding of that because these are mostly hydrodynamical cases, and there are no such thing as solar-like star with no magnetic field. So I will come back to that. So we did some back-of-the-envelope calculation in a 2017 paper where we have an idea on how the Rossby number can scale as a function of mass and rotation, and we will implement that in Plato. You know that we have in Europe, we are working on building a kind of big Kepler called Plato, and we need to have some ideas on what will be the type of differential rotation profile we can expect. So here I show you a regime diagram plot where as a function of the rotation rate from a 10th solar to 10 times solar and the function of mass from half solar mass to 10% more massive than the sun, we have evaluated where is the transition between anti-solar-like stars, solar-like stars, and Jupiter-like stars. So this is just some clues. And also, we have, of course, the meridional circulation, and the meridional circulation is found to be highly multicellular. So this is still something to be looked for. So we looked at some energy balance and trying to understand how much of the luminosity of the star can be used to maintain the differential rotation. And we find that it can be of the order of few percent. For the sun is about 5%. And we find some cases when we put that as a function, this is as a function of the star's luminosity. So of course it varies a lot, as we have seen, from 4% to twice solar. But if we put everything back to solar luminosity, we can reach up to 20%. Well, these are just numbers to give you an order of magnitude. So we know that when stars rotate faster, they get a stronger toroidal field. So here we go from solar to 4 times solar, and you see more stronger differential rotation. And we have now all the 15 simulation with magnetic field, and just the only things you need to look at are the red lines. The black lines here these are cuts as function of latitude and radius. So here near the equator and here near the pole. And you see that when we put magnetic field, we tend to see, these are the red lines, tend to have a weakening of the differential rotation. So there is omega quenching, if you want. The field, the Maxwell stress feedback on the flow and reduce the differential rotation, at least for the solar-like case. For the anti-solar-like case, surprisingly, it then tends to do the opposite. So here again, you can look at the energy flow map, and you can see through the omega effect, when you have differential rotation, you can get toroidal magnetic energy, can advect the field, and you have ohmic dissipation, and you start understanding how all that gets together, and you can assess the amount of magnetic energy that can be created by a star given its luminosity. So we just to do a summary, so Matthias a few years ago proposed that a tenth of the solar luminosity can be injected into generating magnetic field. In our larger parameter study and in 3D, we found that it can be a bit more, perhaps 1% of the solar luminosity. But anyway, this is the ballpark, you know. Thank you, I'm almost done. So when we look at what happened when you put magnetic field, you indeed find that the differential rotation as a function of the rotation rate weakens, and the dependency is not as strong as with the hydrodynamical case. And we get closer. So here, these are not considering all models. These were a preliminary study, and we are getting even closer to the observations. In a parameter study that we did with Paul and Antoine Strugarek, following the science paper of 2017, we found very interesting parameter regime that I want to tell you about a little bit more. We were able to find long cycles, like decadal long, like I showed you the simulation of. We were able to find also short dynamo cycles, sometimes even, like in this case, 06, long cycles, and when you filter the long cycles, shorter cycles. And in the anti-solar dynamo case, anti-solar in terms of differential rotation, slow equator, fast pole, we were finding a steady dynamo. So here in this plot, we show the ratio between the differential rotation and the kinetic energy. And we were able to find a tendency for explaining where we expect to have the short cycles for very low Rossby number, where we expect to have solar cycles that are in a decadal length, like solar-like, which will be in intermediate numbers of Rossby number. And we lost the cycle when we go too slow in rotation. And we, following some proposition from Travis Metcalf and Jennifer Van Sanders, that could eventually, we could lose what we call gyrochronology past the age of the sun. So you know that the sun spin down as a function of time, and there were some intuition that maybe this transition and change of behavior could be around Rossby equal 1. And we know that Rossby equal 1 is when you go from solar to anti-solar differential rotation. And the question was, in a dynamo, when you go from solar to anti-solar, what do you see? Do you see a collapse of the dipole? Because if you see a collapse of the dipole, suddenly the lever arm of your wind breaking reduces and shrink. Okay, so if you maintain the dipole and the quadrupole in your star when it's anti-solar, you don't expect the breaking of the wind to be smaller. And indeed, here we have computed what we call F-dip, the fraction of the dipole with respect to all the other modes. And we find in the solar case values that go. So here we have the 15 case plus the gray dots are 17 cases from using the ULAC code. So here we are result coming from 2 different codes. And over this sample of 32 dynamo solutions that probe the parameter space of various stars, we see that the anti-solar case, which are the red diamonds, doesn't seem to be showing any collapse of the dipole and quadrupole. So it cannot be the magnetic topologies that explain the loss of magnetic braking, at least to the extent of what we can say. So I'm going to skip the conclusion, more or less we start. I want just to say a little bit about going beyond current approaches. As Yuri said, maybe we want to also see some perspective. And I want to say that there is a problem in all this very nice simulation that I just show you, that we don't have any sunspots. So I've started calling that the sunspot dynamo paradox. Is that we are able to reproduce very nice cyclic dynamo solutions, but we have no sunspot in our solutions. We have first results with a former student of Yuri, Nick Nelson, and work we have done subsequently after, some omega loops, like you have seen in the movie also, that can be formed and can be at the origin of sunspots. But right now, we haven't such sunspot being formed. So with that, with the convective conundrum, we decided with Laurent, Matt Carlson, Vassili Arsakantis, Fernando Moreno-Ensartis, and myself to propose for a synergy grant. And the synergy grant are a very big proposal you can get in Europe, 6-year project, more than 10 million euros funded, and to tackle this problem. And what we want to do is to couple Bifrost and Muram-like simulation with ASH. And we want to develop the new global 3D simulation code that could go from the Taco Kline to the low corona. You know, this is very ambitious, but we have the funding and the money to do that. And we will have a 1-month gathering in March 2020 in Paris at the Institut Pascal. So if you want to join us and work on a tough solar dynamo problem and convection and low corona and flux emergence, you're most welcome. Just contact me or Laurent. And just to finish, thank you, Mike and Kate, for all the discussion, good time, wine and food testing over the many years. Thank you very much.
Questions? Lunch? No? What about, say any words about the idea that there's a surface dynamo creating the spots and a deep dynamo creating the cycle? What's your opinion on that?
Yes, thank you for that question. I think that's one of the reasons why we wanted to do this whole sun project, was that we are not yet clear to us if the sunspots are needed to get the 11-year cycle. But the problem is that we cannot address that with numerical simulation. I mean, self-consistent numerical simulation, not just flux transport at the surface. And so that's one of the questions I want. Right now, I don't know if sunspots are an essential ingredient of the 11-year cycle dynamo or just a surface phenomenon. And that's what we want to tackle. We really want to be able, and we think that we start seeing these omega loops and magnetic ribbons in our simulations, but we don't have a photosphere in our simulations. So they cannot pierce through the surface and create spots and being advected by the meridional flow. So we are missing this piece of dynamics in our simulations. So that's why we are trying to build a new code, because we need to go through, very compressible medium at the latest layers. And the code we are using right now cannot deal with compressibility. So that's why we want to do.
A dang surface again.
Yes, definitely. Thank you.
Well, Sharbani showed us some things where she was reasonably content that models agree and maybe they don't agree, and we fiddle with the opacities. But it's interesting, where we have not made contact in any way is between the dynamical models and the dynamo models and what's the nature of the convection zone. It's still basically a hydrodynamic, very bland convection zone. Have you any comments on how the future might evolve, where some of the dynamics, the magnetism and so on, might also be incorporated into the helioseismic inferences?
So in the helioseismic inferences, I guess that, yes, maybe you should need to do inversion with magnetoacoustic waves and not just acoustic wave, but I think there is people like Paul Kelly that have looked at that from the helioseismic theoretical point of view. From the point of view of modeling secular evolution, we were just discussing that yesterday with Kyle, going back from the cocktail we had at Kate's house. And I think it's time to move to perhaps 2D stellar evolution model, where we could be able to take into account some of these processes with more fidelity by learning from 3D models. But we are not yet ready to do 3D secular evolution cases, but we can certainly do secular 2D stellar evolution model. And I think we are ready for that. So that's one of the things I would like to see, is to start having simulation of stellar evolution that include the spin down and recirculation and mixing in 2D. This will be an intermediate step, and I think we can manage with implicit time stepping or spectral time stepping. We can certainly be able to advance simulation over secular time scale in 2D. So that will be where I will like to go in some aspect of modeling.
Last question in the morning goes to Charlie.
Yes, that was a great talk. I understand that there's evidence, recordings by Cassini in the Renaissance, that suggests that during the Maunder minimum, the dynamo doesn't so much shut down, possibly, as just the surface manifestation of it disappears. And so I wonder if you could say something about that.
Yes, definitely. I mean, that's what we have been discussing in various people who are doing models with Mosumi, with Matthias and few others, is what happened, or Hideo Kyoto. I mean, what happened when during the Maunder minimum, where you have very few sunspot and active regions. So I did do an observational work. I'm not an observer, as you know, but I work with Thierry Roudier and Michal Zvanda to try to see by using current magnetograms, if we could see to high latitude some pores, and maybe during the Maunder minimum era, where we were starting to do some observation of the sun, because it started with Galileo, they were missing small magnetic structure. And maybe some of the small magnetic structure could have some correlation that could eventually replace the large-scale active region or bipolar regions. We did find some correlation. It's not easy. It was done with the current sun and not a minimum sun. But it's difficult to say that if you could get or not a surface reversal of the field by structures that are more diffuse or not as large than active regions. It could be a kind of way of backing up this Babcock-Layton process of having the reversal due to the tilting of the field on inactive regions. So there is eventually an alternative during Maunder minimum state to have perhaps small structures that will do the work of advecting the flux there. But it could also be that the sun is showing us during the Maunder minimum that it doesn't need the spot to reverse. And Beer in 98 clearly showed that in the ice core record, he sees the 11-year cycle still going on, you know. So I think this is still a question that is pending, and that's why I want to do this new model where I have the corona, low corona chromosphere and the convection zone to be able to see, do we need the spots or not to get the cycles, you know? And that's wait and see.
Okay, let's thank our speaker one more time. And we have announcements from a leader.
So there will be lunch available in the atrium. Places to sit to eat lunch would be in the back of the atrium. There are some tables. Outdoors, there are tables. And upstairs above the cafeteria on the second floor, there are also places to eat lunch. So enjoy, and we'll reconvene at 1:30. Thank you.